look a little bit better for you. All right. And we'll lock it down. There we go. Okay. All right. So this is a big lesson. It's going to take a while. So, and it's an important lesson, though, because we get into the preliminary discussion about how we find areas under a curve, which is exactly what an integral is. And the section is labeled the area problem. This is directly tied to our summations that we worked on in Chapter 9. So there's some important, a couple of important properties here and formulas that I asked you to memorize. I don't know if you still know them or not, but I want to make sure that you have got this down. So the first summation property involves this, where C is a constant, like a number. And if we think about what the summation process means, it means that that's my starting point, that's my ending point, and that's what I'm adding. But since it's a constant each time, it just really means that we have we're adding C n times. So we have n number of C's that we're trying to find the sum of. So in this case, when you do C times or plus C n times, we know it's the same thing as multiplying n times C. Or an example of that would be if I have I goes from 1 to 10 of, say, 5. We know that that means 5 plus 5 plus 5 plus 5, and there's 10 of those. So this is just 10 times 5, or 50. So anytime you have a constant, you can just multiply the constant by the number of times we're adding them together. Okay, next important property that we have here is, let's say I have I goes from 1 to n again of C, which is still a constant, now times I. So this is like in 12.4, that's the property I was starting to get into, and then I said we'll come back to it in 12.5. So here we go, we're coming back to it. In this particular case, we know that this means, again, this is your starting value, and this is your ending value. So the first time I is 1, so we have 1C, and then I becomes 2, then I becomes 3, all the way until we get to n. But if we notice in each one of these terms in the sum, we have that constant, which means this can be factored out. And we have that happening. This then just becomes the sum of the integers from 1 to n, which, if we remember, that is nothing more than an arithmetic series. So we have n plus 1 times n over 2 for that particular formula. Those are the summation formulas that we have. So as we start out here, what I would do, and in this section, what you always want to do is to take any constant and pull it outside of the summation. So really what we're doing here is we're looking at the sum of the integers from 1 to n, which we know is n plus 1. Again, first plus last, right? And we have over 2. So that's just Gauss's formula. And so this is how we can evaluate the summation by taking out the constants. So, and we've done this, right? All of this should be review for you, just like when we take a summation of any old polynomial, as I goes from 1 to n of, say, 2i squared plus 2i plus 3. What did we do? If you remember correctly, we took and broke up the sum. So we had 3 different series, and this is very similar to the limit of the sum equals the sum of the limits, right? So we're going to do that in each case. So we break up the polynomial into 3 separate sums, and then using the property that we described above here, we can take this 2 out front. Take this 2 out front, and we know this is just 3n, and that's from this up here. So we have the sum of the integers squared and the sum of the integers, which we had formulas for. And so I'm going to go over those formulas right now, just to make sure that we remember them. So the sum of the integers from 1 to n, again, that's just Gauss's formula, n plus 1 over 2. The sum of the integers squared from 1 to n is n plus 1, 2n plus 1 over 6. And what's difficult, I know it's been a long time, but again, these formulas can be found and proven through the induction process. Right? We can look for the patterns, prove it through induction, but this is the formula for this particular sum. So you might want to go back into your notes and kind of take a look at that and refresh your memory about what's going on here. But now we're just kind of jumping to the formulas. We're going to use these. And then we have the sum as I goes from 1 to n of the integers cubed, which, if you recall, is just that formula squared, right? So we take n squared, n plus 1 squared over 4, which some of these, again, you would have seen in the homework in 12.4 and the examples we did in the notes from 12.4, because that's why they popped up, because we're going to use them. All right, so again, this stuff's important, and we're going to use these formulas in conjunction with limits at infinity, which is what we did in 12.4. You might be asking yourself, these don't have any limits at infinity. True, but when we incorporate the summations with finding the area under a curve, they will, because there's something else that comes into play. All right, so that's sort of the background information. If you feel comfortable with that, we're going to move into the area problem now. And so what I want to look at is, how do we take a function, let's just take a simple function like x squared, and find the area under that curve? Well, let's take a look at that curve. All right, and what we see is, if I'm looking at the area under the curve, well, that's infinite, right? That's everything that's under that curve. So we have to bound it. We have to put some boundaries on it. So what we say, and what we're going to look at, and when you get to calculus next year, you could bound this with the y-axis, you could bound it with the x, you could bound it with another function. We're just going to keep it simple for now, and we're going to look at this kind of a question. So we're going to find the area under the curve of f of x equals x squared, bounded by the x-axis on the interval 0 to 3. So again, that is the interval 0 to 3. So we're going to look at finding the area from 0 to 3. So really what we're looking at, again, that's x equals 3, is we're looking at trying to find this area right in here. So probably if we were in class, I would just throw you that problem and I would say, have at it. Go ahead. Work together, investigate. How would you do that? Back in geometry, if I remember correctly, some of you would have taken a look at maybe, you got this lake. And how do you find the area of the lake? And one of those processes would be to throw a grid over the lake, right? And then if each of these squares represents a square mile, you would say, okay, I've got 1, 2, 3, 4, 5, 6 6, 7, 8. I've got 8 of those squares that are completely inside the lake, so there's at least 8 square miles. And then you have all these that are on the boundary, and you would take a look at that, and some are more than half, some are half approximately, some are less than half. So the idea is take all the boundary squares, count them up, and then take half of those and then add that to 8, and you get a pretty decent approximation. Not great, but what would make it better? Well, to make it better, we would start cutting those squares half, right? So in this particular case now, we've got a lot more inside, but now each square represents a quarter of what it used to, right? It's 1/4 of a square mile. So you count those, and then your boundaries also increase, but you have less area that you're losing. So to even get more accurate, you keep making these squares smaller and smaller to get more and more accurate. And again, this process is kind of what we're going to do to apply to this. Okay? So we're going to go ahead and take a look at my figure. I'm going to make this big. Alright, so here's my interval. And this is the area that I'm trying to find here, right? That particular is y equals x squared. Okay, so I'm going to just use the idea of rectangles. And remember, to find the area of a rectangle, it's equal to its width times its height. And I'm just going to use rectangles here to see if I can determine the area under that curve, bounded by the x-axis on the interval from 0 to 3. So to start very simply, I'm going to put in 3 rectangles here. So I'm going to put one here. And you notice I'm going to the right end of that rectangle, stopping at the function. And here. So this part of the rectangle right here, right, is under. So I've got some overage, which is okay for now. Okay, but the idea is if I find the area of those 3 rectangles, I get an approximation of what I'm dealing with. First thing we have to pay attention to is, though, what I did is I started at 0, so each width is going to be the same. The width has to stay uniform or constant. That's important. Okay? So to find the rectangle width, I took the interval width, which in this case is 3, and then the number of rectangles that I want, which was also 3. So we see that in this case the rectangle width is 1, which you see that each rectangle is 1. But if you notice, the rectangle heights are changing, and they're changing right along with the function itself. So the height of each rectangle, which I need, is dependent solely upon the function. Right? So in each case, those points have xy values. And the y values represent the heights of those rectangles. So as we go along the interval, I need to plug in the right endpoint values, which are the x values, at the right end of the rectangle, into the function to determine the height of that rectangle. So the first right endpoint here is 1, and when I plug 1 into the function, 1 squared is 1. Right? When I do the same, now I'm going to take from here and I'm going to add another width, which gets me to 2. Right? So I went 1 width, 2 widths. Right? This is 2 widths. That's important. And I'm going to plug 2 in then, and I get 2 squared for my height. So this is 1, this is 4, that's the y value, right? 2, 4. and then 3 widths. I plug in 3, and I get 3 squared, which makes this 9. So my 3 areas are 1 times 1 plus 1 times 2. And you notice I'm not using 2 because I'm not using this big rectangle. I'm just using the width. I'm just doing each individual rectangle. So my width is 1 times 4 plus 1 times 9. And again, the 1, 4, and 9 just represent the y values of the function as I move along my interval. So, and you can see we're adding areas of those rectangles, and this is where the summation process is going to come into play. For now, I have 1 plus 4 plus 9, which is 14 square units. Again, like the lake example, right? Not a great estimation because we have all of this which isn't under the curve. All right, so again, just an approximation is what we have here. All right, so how do we make it better? We make it better by more rectangles. So we can have any number of rectangles we want, but for the sake of this example, I'm just going to say, what if we cut each width in half? In other words, instead of having 3 rectangles, let's have 6. So going back up here, my interval width is not changing, right? So my new rectangle width becomes 3 is my interval width over 6 rectangles gives me a width of a half. So in my drawing, what we see is I'm cutting each of these in half. So now it's obvious to see that I've got 6 rectangles to find the area of now, right? But if you notice, those 3 areas right there are now gone, right? In this new example, they don't become part of my overage anymore, so my approximation gets better. But instead of multiplying each rectangle by 1, I'm going to multiply each height by a half. And now I have 6 different rectangles I have to find. And as I move along my interval, what I'm plugging in to find my heights are a half, 1, 1.5, 2, 2.5, and 3. So you have 1, 2, 3, 4, 5, 6 different heights times a half. In each case, the constant, right? So the width of the rectangle is the constant here. And then we get a new approximation, which will be less than 14, but still not accurate enough because we have these overages right here, right? So, but it is better. All right, so let's take a look at this process. If we could, sorry, just getting some more paper here, bear with me. Okay, I'm going to go ahead and go back to my function, right? On the interval from 0 to 3. And looking at this, how could we make this more and more accurate? And the answer is increase the number of rectangles. The more rectangles, the less overages, right? I mean, if we get something very small, if we do a half, and so forth, then the overages start to disappear. And the rectangles start really filling up the area under the curve. And that's what we want. So the best case scenario is to have infinite rectangles. Because with infinite rectangles, we can assure ourselves of getting very, very accurate. All right? But when we go to infinite rectangles, and this is the important part, what happens to my width? I mean, I can't take 3 and divide by infinity because that doesn't work, right? It's almost like when we did our derivative, what did we do? We let the change in x in our slope formula go to 0. So we no longer could do that. We had to use a limit. Same thing has to happen here. But instead of the limit as we're approaching 0, now we're looking at the limit as the number of rectangles is going to go to infinity. Hence, all the work you did in 12.4. Okay, So again, let's see how that process works. So we're going to look at just what happens when we have n rectangles. We're going to do this in general. So, first of all, what is your rectangle width? Again, my interval width over your number of rectangles. In this case, my interval width is 3, and I have n rectangles. So each rectangle is going to have a width of 3 over n. If you remember when we did 6 rectangles, my width became a half. If I had 12 rectangles, my width would be a fourth, and so forth. Right? So you see the width of that rectangle heading towards 0, which is why this process works. Okay, so then what is the area? Right? The area is going to be the width of the rectangle times the height. So in this case, my width is 3 over n. And the height of each rectangle, we remember, is function specific. Right? So we're going to have to take f of 3 over n each time, right? So this is changing. So what we need to do is to use a series, because when we have our one width, then we have to add on 2 widths, and then 3 widths, and 4 widths. So what I'm saying here is to find the first height, we got to add 1 width. To find the second height, we have to add on 2 widths. The third height, 3 widths. The fourth height, right, we plug in 4 widths into the function, which is what we're doing here. So as we move along, we have to keep adding on the width to the x value into the function. So this is what we look at here. My area becomes my width times, as I goes from 1 to n, times f of 3i over n. Alright, so let me explain that, right? So what's happening here is we have, when I is 1, this becomes 1 width. So we plug in 1 width into the function f. When I is 2, this becomes 2 widths. So we're plugging in 2 widths into the function. So this is, every time I changes, we go up 1 width. And so we're moving right along that interval. And we're adding in the right endpoints of those rectangles to find the height. So this, again, represents your height. Now, the real question here is the width changing? The answer is no, right? It'll change depending on the number of rectangles, but every time you do this problem, you're going to have a set number of rectangles. So if we did this problem with 6, this would stay a half. So your width doesn't change. So it's a constant. So if you remember what I talked about when we were doing these, pull that out. First thing you want to do, right? So we're going to take a look at, and really what ends up happening here is we're taking the width of the rectangle and we're just summing all the heights. And we're going to do one multiplication instead of multiplying each height and then adding the area afterwards. Okay? So now we have this. So the next step then is to go ahead and plug this into the function. So plugging 3i over n into my function that is defining the height, so this becomes 3i over n squared. And we get, and go ahead and square this. So the rest of this is really some algebra and summation properties. So we have 9i squared over n squared. And what we want to do now is isolate the I squared. So we're going to pull out the constant. So we have 3 over n times pull out the 9 over n squared times the sum of the integers squared. Alright, so why do we need to know these formulas? For right now. Right, this is the whole process, the whole time we need to do that. Alright, so I'm going to flip this over and we're going to continue. So I have 3 over n times 9 over n squared times, and now we need the formula for the integers squared, which is n plus 1, 2n plus 1 over 6. So if you're looking at this particular expression right now, what we see is an n cubed on top and an n cubed on bottom. Remember what we want to do, right? We want to find the limit with letting n go to infinity because we want an infinite number of rectangles. Before we do that, right, I think it's important that, let's say, what is, if we let n be 3, do you remember what we got the first time when we had 3 rectangles? We had an answer of 14 square units. So if we let n be 3 and we evaluate, we get 1, 3 times 4 times 7 over 6, which is, this is 1/2, and then this is 2, so 2 times 7, 14 square units. Right, so this particular formula worked when n was 3. If I plug in 6 for n, it will tell me what the area is of those 6 rectangles. So my summation is adding up all the rectangles, right? So this is a general form. So now what is my goal? My goal is to let n go to infinity. So what is the limit as n approaches infinity of 3 over n, 9 over n squared, n plus 1, 2n plus 1 over 6. Because now the idea is we can have an infinite number of rectangles, which is going to give me the limiting value of the process of increasing the number of rectangles, which will give me the exact value of the area under the curve, right? So remember, this now just becomes the same kind of problem that you did in 12.4. We have n cubed on top, we have n cubed on the bottom. So what are we looking for when the degrees are equal? The leading coefficients. So be careful here now. You have 27, and you also have this too, right? You got to multiply all the numbers that are in front of the variables or the constants out front. So this would be 54 n cubed on top, and on the bottom we have a 6n cubed, which again, those don't matter. So 54 over 6 would be the limit of this particular expression, or 9 square units. So that is the limit of that particular function, or infinite rectangles under the curve. So this represents the area under f of x equals x squared from 0 to 3 bounded by the x-axis. So remember, our first estimation was 14. The actual answer is 9, right? That is the exact answer. In calculus, you will see that written like this. That is an integration symbol. It's like an elongated S, because what are we doing? We are summing the areas. Left endpoint of the interval, right endpoint of the interval. My function, and then that dx sort of says with respect to x. So this is kind of showing off your boundaries, and that's the function. And that's asking you to find the area under the curve on the interval from 0 to 3 with respect to x. Okay, so I'm going to show you a neat little trick, right? This is the only time I'm going to show you this. We don't do a lot of integration in this class. We do more with derivatives than we do integration. But the integration piece is the antiderivative. What do I mean by that? I'll come back to this page in a second. So let's say my function is 4x cubed plus 12x squared minus 6x plus 9. The derivative using the power rule. Right? The derivative using the power rule is to take the power times the coefficient and drop the power 1. Right? So this becomes 12x squared plus 24x minus 6. And remember, that constant's just gone. So this becomes the derivative. So the antiderivative would be to go backwards. Right? Remember, we found this 12 by multiplying. So the idea for me to be able to go backwards in this particular case would be to add 1 to the power, and again, we got to go in the reverse order, right? So instead of multiplying and subtracting, we're going to add and divide to do the antiderivative here. So x to the third, right? So this becomes 12x to the third over 3, dividing by the power, right? This becomes 24x squared over 2, dividing by the power. This becomes 6x to the first over 1. And the only problem here is that I don't know what the constant is because it's gone. So I just kind of do plus c. So what do we end up with? 4x cubed plus 12x squared minus 6x plus some constant. So if you take a look, we can go forwards and backwards. Okay? Interesting concept. Interesting concept. Let's go back to this particular problem here. So my function, right? If I wish to integrate, what if I did the power rule here backwards? Right? So I have 1x to the third over 3. Then if I take my top number and I plug it in, right here, I get 3 cubed over 3, and I subtract my bottom boundary, 0 cubed over 3. I end up with 27 over 3, which is the answer. So what does this mean, geometrically speaking? This means that when we take a look at the connection between an integral and a derivative, right? We take a function, when we do the derivative backwards, we find its integration, or it represents an area under the curve. Much like when you take a look at a position function and you find its derivative, you get its velocity. Right? But when you go the other way with it, you find that area under the curve, which might represent, the amount of space that it's traveled or whatever. Something else that's sort of interesting before we move on with this lesson, some formulas that you know, right? We know that the area of a circle is pi r squared. If we were to perform the derivative on this, so a prime is 2 pi r, which represents its circumference, right? So the area, this is a linear measurement, right? This is a area measurement or a second unit measurement. So linear measurement, distance around that circle of radius r, area of the circle. Now what happens if we go in the other direction? In other words, we find the integral here. So we do the antiderivative of the area. We got pi r cubed over 3. right? This goes up 1 and divide. So we end up with this should be a 4. So what did I do wrong here? Pi r cubed over 3. So forgive me for this should be 4. It's the volume is what it ends up being. So what did I do wrong here? Well, I'll come back to that later. It's not happening for me right now, but I know that the integral of that has to be no, whatever, I'll come back to it. But I know that the integration of the area formula is the volume formula for a circle. So interesting relationships here. Sorry I screwed that up, but whatever. All right, so getting back to what we're having to do. And hopefully by the end of the lesson that'll dawn on me what I did wrong, but that's okay. So you need the function, you need an interval. So I'm going to take a look at this again. But let's say my interval went from -2 to 3. So now, instead of going from 0 to 3, I'm going from -2 to 3. And how does that affect things? What we're looking at now is finding all of this area, right? So now my interval becomes, my interval width becomes 5, because it's 3 minus a minus 2, right? And let's just say we go with n rectangles. The difference now is that for me to be able to find this y value, I have to start here. So we know that my rectangle width with n rectangles is 5 over n, because I take my full interval width and divide by the number of rectangles. And then I have to multiply that by all the heights as we go along. So my area becomes my width times my height, which is this now. And again, because I'm not starting at 0, I'm starting at -2. And then I start adding my widths to get to that right endpoint. So that becomes 5i over n. So the last time we just did 3i over n because we were starting at 0. In this case now I'm starting at -2, so that's my starting point, plus 1 width, starting point plus 2 widths, starting point plus 3, plus 4, and plus 5. So we have a starting point here, so we have to translate it over. So the next process then would be to let I go from 1 to n. Remember that's a constant, so we must pull that right out immediately. And then we have f of -2 plus 5i over n that we have to deal with. Okay, that being said, we go ahead and this is a part where a lot of kids screw up, is that they just start looking at this. But again, we have to plug this into the function before we do anything. So the next step would be to plug this particular guy, this expression, into my function that's generating my curve. So it's -2 plus 5i over n squared. And then we're going to go ahead and rewrite this over here. That's why I needed more paper. Told you this was a big lesson, so I apologize. I'm really trying to walk you through it so that you understand what's going on. I'm going to go ahead and expand this. So I have 5 over n times the sum as I goes from 1 to n of, we got a 5i squared over n squared. 2 of those, right? So -20i over n plus 4. Okay, so that's foiling, and what I did is flip this around. Which is where this came from. So you got, oops, good thing I looked at that, 25I squared over n squared. A minus 10I over n and a minus 10I over n is negative 20. So this is that product, right? And then now, before we can start to evaluate this, we need to split these up. So yes, there's a lot of work involved here. So I have, and as you go through, right, I'm going to split each one of these up into their sums. But you can go ahead and pull the constants out front while you're at it. So the 25 over n squared is a constant. Anything with an n in it's a constant. Anything with an I in it is not. So that leaves that. And then we got a minus 20 over n as I goes from 1 to n of I, plus I goes from 1 to n of 4. So splitting these up, pulling the constants out, okay, and now we're ready to use our summation properties and our formulas to get rid of those. So we have 5 over n, 25, and then I squared is n squared, n plus 1 squared over 4 n squared. Right, so this is that formula, minus 20, and then I, oh, well, I'm really sorry. This is not the right formula. I'm sorry. I don't want to have to restart this whole stupid thing. Again, the formula for I squared is n plus 1, 2n plus 1 over 6. So some of you are probably watching and going, no, that's not right. And it's not. Sorry, that was the I cubed formula. My bad. Okay, so the I squared formula is this. Okay, and then we got negative 20 over n, and then this is n plus 1 over 2 times n. And then here is just 4n. Okay. Apologize for that. Alright, so again, this formula, n plus 1, 2, n plus 1 over 6 times n squared. And then this formula is n plus 1 over 2 times the negative 20 over n, and then 4n. Okay, and then I guess what I would do, if it were me, is I would go ahead and distribute that 5 over n. So we have 5 times 25, or 125. And I'm not going to go ahead and do any more multiplication than that. So I've got a 6n cubed minus 5 times 20, which is 100, over 2n squared, right? So I'm just distributing this plus 20n over n. So again, let me double check. 5 times 25 is 125. Awesome. Go, Mr. Lampkin. 5 times 20 is 100. I think that's right, too. Okay, so you can see, again, there's a lot of room for error. So you got to make sure you keep double checking yourself. Okay, so what do we have here? So now, this is the expression that represents the area under the curve here for n rectangles. So if I had asked you find the area with 10 rectangles, you could either plug 10 in here and do this specifically for that, or you could go to this general case, plug 10 in here, and give me the answer. Which, if we were taking a quiz or a test, that's what I would do, because it forces you to go through this whole process. Okay? And if I, said, okay, do 10 rectangles, do 20 rectangles, and then do infinite rectangles, it would make sense to do this once, because at the end you could plug in 10, you could plug in 20, or you can do what we're going to do now and take a look at the limit as n goes to infinity to find the actual area under the curve. Okay? So, taking a look, we have n cubed over n cubed, we have n squared over n squared, we have n over n. So we're in good shape here as far as finding the limits of these three. And remember, the limit of the sum is the same as the sum of the limits. So I'm going to find the three limits and combine them. Keep in mind, there's a minus sign there. So in this case, my leading coefficient here is 250 over 6. So that's the limit of this guy. Here I have 100 over 2, and this is 20. So we have 250 over 6 is 125 over 3. So 125 over 3 minus 30, which my brain hurts. So 125 over 3 minus 30 is 35 over 3, or approximately 11 2/3 square units. So notice what we did here. There's two big things that are different about this, is that we took, and instead of starting at 0, we started at -2. So I moved the left endpoint of the interval. So to find the interval width, we took the right endpoint minus the left endpoint. Divided by n, this becomes my rectangle width, right, with n number of rectangles. And then when we went to find the actual heights, we have to start here. And remember, we're using right endpoints of the rectangle. So I start at -2, add 1 width, right? Then I go -2 and I add 2 widths. And I go -2 and I add 3 widths, etc. And that takes me all the way up until I get to the right endpoint of my interval. So we set this up. Then we had to plug it into the function, and then we can start our summation process and then look at our limit. Okay, so in general, what do we got going on here? So we have a function, some function, right? And let's say our function is f, and my interval could go from a to b. So if my interval goes from a to b, that means my interval width is b minus a. So my rectangle width for n rectangles is my interval width divided by n. So that is my rectangle width. All right, interval width, rectangle width. And then a is my starting point, and that's important to remember. So when we start talking about the area, I take my rectangle width, which is b minus a over n, which remember is a constant, and I multiply it to my heights, which to get the height or the y value, I need to plug in my right endpoint of each rectangle into the function to get the y value or the height of that particular rectangle. So I take my starting point, which is a, and I add on iterations of my rectangle width, which is b minus a times I over n. So again, this is my rectangle width, which you're going to find first. Starting point, plug it into whatever function we have, and then you move along. So we are summing as I goes from 1 to n of my width times my height. Starting point plus first width, second width, third width, as we move along from left to right along the interval, right? And so again, this is a constant. So what I'm going to tell you to do is pull that out first. So that's the very first thing you should do, is take that b minus a over n. Let I go from 1 to n of this guy. And then based on whatever your function is, the next step would be to plug this into that function. And then you have your summation. Start breaking up your summations, pull out all your constants, apply your formulas, evaluate your limit. All right? So plug height into the function. Separate summations. Evaluate limit. And you find your area. It's a big process, right? Hopefully you followed along all of this. So what I'd like to do now is just sort of, and in the, in some of the problems in the homework, they're going to take you through various pieces of this. So what I'd like to do is just kind of go through a couple of examples with you. I know this is a long video already. We're at 51 minutes. But this is why we break this up over 3 days normally. Which is why, like I told you on during your class period, when you get this on Monday, when you're looking at this video, get 12.4 done right away and start working on 12.5. Save the week for 12.5 because it's going to take you some time. You're going to fumble through some of this at first. That's okay. But take your time, right? Okay. So some examples. Let's go ahead and we'll do f of x equals 2 minus x squared on the interval from -1 to 1 bounded by the x-axis. So we're trying to find the area under the curve. Okay, so first thing, right? Find your rectangle width. So your rectangle width is your interval width, which is 1 minus 1 or 2 over n. So this is n rectangles. So this is your rectangle width, right? So your area then becomes your width, which stays constant, times your height, which is f of your starting point, plus iterations of your width. Right? So that's 1 width, 2 width, 3 width as you move along the interval. So then we bring in our summation. We're going to let I go from 1 to n, because we have n rectangles. If we had 10 rectangles, that would be a 10, etc. So we're going to take my constant, pull it out, and we're just going to deal with this. All right? So that's taking my width and multiplying by each height as we go from -1 to 1. So we're looking for that expression now. So then step 2, plug into the function. So I'm going to do this. So I got 2 minus -1 plus 2i over n squared. So I'm doing this over here, and I'm going to make sure I don't screw this up again. So I'm going to have 2i over n minus 1 times 2i over n minus 1. And then we have 2 minus all that, so foiling here we have 4i squared over n squared. Got a negative 2i over n, and a negative 2i over n gives me a negative 4i over n plus 1. Alright, so coming back to this, we have I goes from 1 to n, and this is here, so I'm going to go, I got a negative 4i squared over n squared I've got a positive 4i over n, because I'm distributing that. And then I've got a 2 minus 1, which is a plus 1. So assuming my algebra was done correctly, which I'm going to double check. So I did 2 of these. Now I have 4i squared over n squared minus 2i minus 2x minus 4i plus 1, negative, positive, 2 minus a minus, or 2. Okay, so we're looking good. Now, the next thing, separate summations. So I have my constant, and again, this is multiplied to this whole thing, so keep that in mind. So not a bad idea to use a bracket here. We have the sum, and while I'm doing this, I'm going to pull my constants out front. So I've got a negative 4 over n squared, I squared, as I goes from 1 to n, plus my constant's 4 over n, I goes from 1 to n of I, plus I goes from 1 to n of 1. So again, I pulled my constants out, and that's these guys. Anything with an n in it is a constant, because we know that number. Constant. And then we're going to bring in our formulas. So we start to evaluate summations. I've got 2 over n, so I got one big fraction, so let's not make that same mistake here. I squared is, I got my negative 4 times this, which is n plus 1, 2n plus 1, over 6n squared, n squared coming from here. All right, so that's your formula for I, the sum of I squared times negative 4 over n squared, plus, and then I've got my 4, and then this is n plus 1 over 2n, and then this is just 1n. Then the next step, I would distribute this guy, right? Bring him in now. So I'm going to go ahead and multiply this to these. I don't really have to, I'm going to worry about that later, but multiply this through here. All right, so next page we have all right, so I have 2 times negative 4, so that's negative 8 n plus 1, 2n plus 1 over 6n cubed, plus 8n plus 1 over 2n squared, plus 2n over n. So what did I do there? I just multiplied all those by that constant that was the width. All right. And now we want to apply the limit as n goes to infinity. So again, the limit of the sum is equal to the sum of the 3 limits. So we're only looking for leading coefficients here. So I have negative 8 times 2. If you notice, we've got n times n times n is n cubed, and all of these are going to be degrees where they're equal on the top and the bottom. So I've got negative 8 times 2 is 16, so I got negative 16 over 6 is the limit here. Here we have 4 and 2. So this becomes a negative 8 thirds plus 6, which is 18 thirds, or 10 thirds. So what does 10 thirds represent? 10 thirds represents, and if you remember what the function was, it was 2 minus x squared. So if we take a look at that graph, looks like this. And we're on the interval from negative 1 to 1. So we're looking at finding that area. So that's 3 3 1/3 cubic or square units. Okay. That's a lot. I think I'm going to do one more. And again, the process never changes here again, which is a nice thing. But what happens when the functions get more involved? And so that can be, just a lot more algebra, a lot more things you have to keep track of. But I'm going to do one more example, and it's number 48 in your book. And it kind of involves everything that we've done. So the function itself is x squared minus x cubed. And we're on the interval from -1 to 1. Okay. So, again, we need to find, and we're going to look at n rectangles, right? So my interval width is 2. So my rectangle width is 2 over n. Because my interval width is 1 minus a minus 1 or 2. And my number of rectangles, so each rectangle is going to have a width of 2 over n. So my area is 2 over n times f of, and then got to find my heights, right? Starting point is -1 plus iterations of my width. So again, what does this do? This gets me to the right end point of the rectangle. Plugged into the function gets me the height of that said rectangle. So the first right end point is going to be -1 plus 1 rectangle width. Plugged into the function gets me the height for that rectangle, times the width is the area of that rectangle. When I is 2, you get 2 widths added on to the left end point, takes you to the second rectangle's right end point. Plugged into the function is the height of that rectangle. Okay, so the next step then is we need to sum all these up, and we're going to take that constant out front. So I goes from 1 to n of f of -1 plus 2i over n. Plug it into the function. So we have this gets plugged in. So now we've got to square it and we've got to cube it. So this is where the algebra gets heavy duty. Oh no, I'm running out of ink. Let me pause the video really quick. I got to find another pen. Okay, I'm back. I got another pen. So hopefully this ink will last. Alright, so we are taking this expression right here and we are plugging it into the function, again, which requires me to square it and cube it. So I'm going to square it first, and again I'm going to flip these terms. So I've got 2i over n minus 1 squared, which is 2i over n minus 1 times 2i over n minus 1. So FOIL that out, we're going to get 4i squared over n squared. -2 is -4i over n plus 1. And then I have to cube it. So I'm going to take 2i over n minus 1 to the third. And again, this is a question that I have put on previous test. And it requires you to be able to square and cube. And remember, when we cube, we'll bring in Pascal's triangle. So 1, 3, 3, 1. Third row. We take 2i over n to the third, 2i over n squared, 2i over n, and to the 0. And then we take -1 to the 0, -1 to the first, -1 squared, and then -1 cubed. So we have 8i cubed over n cubed. We have 4 times 3 is 12. So minus 12i squared over n squared. Don't forget to square that guy. Plus 6i over n minus 1. Alright. And so the function itself is x squared minus x cubed. So I'm taking this and subtracting this, which means I have a negative 8i cubed over n cubed. And then I have 4i squared plus, because it's subtraction, so it becomes 16i squared over n squared. And then I have negative 4i minus, so negative 10i over n, and then 1 plus 1 plus 2. Okay, so a lot of algebra there. So now we got to do what? We got to split all that up. So I've got my 2 over n times, and again we're going to pull out our constants, so negative 8 over n cubed. And this, again, as you start doing this, you see, are we going to keep writing out all those summations? We might just go right to the formula here. All right, so we know we got the sum as I goes from 1 to n of I cubed left here. I'm not going to write it out, but I'm sure some of you are going to quit this. And then at some point, some of you are going to know that formula, and you're going to be able to kind of do this in your head, what those limits are at some point. So I goes from 1 to n of I cubed plus, and then we got 16 over n squared is a constant. And then we got the sum, as those get worse and worse. I goes from, that's I squared. Then we got minus 10 over n. Sum as I goes from 1 to n of I. And then 2n, if I can do that, right? Because it's the sum, that's a constant, so that's just 2n. And then remember what we do at this point. We're going to go ahead and distribute, well, actually we're going to put our formulas in. But why I do that, I'm going to go ahead and distribute this guy at the same time. All right? So I have a negative 16 over n to the 4th times the formula, so this becomes n squared, n plus 1 squared over 4. That's this formula right here, plus 32 over n cubed times n plus 1, 2n plus 1 over 6 minus 10 times 2, which is 20, over n squared. This times that, right? Times that, which is n plus 1 over 2. And then, sorry about that, 4n over n. Should have made that a little smaller. Take a break, shake your hand out. Okay, so now what do? We apply the limit as n goes to infinity of all of this, right? And you can rewrite all this, but we know, what do we need here? We only need our leading coefficients. What are my leading terms going to be? That's an n squared, that's an n squared, so that's n to the 4th. So really, what are we talking here? We're talking 16n to the 4th over 4n to the 4th, but it's negative, plus 32 times, don't forget that 2 here, so 64n cubed over 6n cubed minus 20n squared over 2n squared. And all I'm doing is writing those leading terms, plus 4n over n. So we have negative 4 plus 32 over 3. All right. As we apply the limit at infinity, minus 10 plus 4. So that is gone. So this 32 thirds is really 10 and 2 thirds minus 10. So that is what we end up with for the area under the curve from negative 1 to 1. And that's one problem. So just the highlights here again. What do we have? We have the interval. We have to find the interval width. Remember, the interval width was 2, right? 1 plus 1 is 2. And rectangles, if that's what we're using, that becomes my rectangle width. So my starting point plus iterations of my rectangle width create all the heights as we move from left to right along the interval. So we need to sum all those. Then it's a question of doing all the algebra. Whew. All right, big lesson, big lesson. So hopefully, gang, that makes some sense to you. It's until you actually get into it and start doing it, you'll see some places where you can kind of, like you are going to get to this point when you know these formulas that you're just going to jump right to these limits and be able to do this a little bit faster. This is kind of, if you're going to make a mistake, it's probably going to happen there. I will tell you, if you were sitting in a regular pre-calc class, your lovely pre-calc teachers would force you to simplify all this into one simple fraction. To me, I've always argued that that's insane and not necessary. And it undercuts the concept of what a limit at infinity really means. I mean, all we care about are the leading coefficients because that's the value that it's going to approach. So it kind of, you lose the forest from the trees when you do that. But anyway, it's not me. It's not how I operate. It's not how I want you to think. I want you to maintain all the major concepts here about what's going on. Okay, I'm going to pause for a second. Okay, just a little tidbit on what I was stuck on before. I realized that I was operating interdimensionally, which you cannot do. So that's my bad. Because I was mixing circles and spheres together in my mind. So you can't do that. So let me go back. When you have the area of a circle, which is pi r squared, when you take its derivative, right, using your power rule, 2 times pi, drop the power 1. So the area, its derivative, becomes that circle's circumference, right? And when we take the circumference and we integrate it by doing the antiderivative, the power goes up 1, so we get 2 pi r squared, and then we divide by that power, in which case we end up back at the area. When you're talking spheres, right, this is for circles, when you're talking spheres, the surface area of the sphere is 4 pi r squared. When we integrate that, we get 4 pi r, we up a power, divide by the power, we get that, which is the volume of a sphere, right? So the idea is when we find the derivative of this, we get its surface area. When we integrate it, we get its volume. So there's a definite connection. Obviously, we can't go from circles to spheres. They're two different shapes. That's why I was stuck there for a moment. Couldn't figure out what was going on. But I did want to clarify that. And I think that's an interesting thing to understand what's happening as we go from these formulas and we integrate them, we see where their volumes come from and so forth. So for some of you people, when you want to take a look at other formulas to see how that works, they're all tied together. Okay, that's the end of lesson 12.5. Good luck. Highlanders, for you seniors, we're gonna move on with our derivative unit after this, so there'll be a bunch of worksheets, but there'll still be some video lessons, and how we integrate, they'll just be a lot shorter than this. And then for the rest of you, once we finish that derivative unit and the seniors are gone, we'll jump back into 11. There's 4 sections in 11, which is 3D vectors. Okay. I'm done. Have a great day, Highlanders.